Welcome, ladies and gentlemen. The point of today's Bellwork was to make a connection between the inverse operations you use to solve a normal algebraic equation, like in number 1, with this trigonometric equation, where we had to find missing sides and missing angles. On the quiz, right, the trickiest one, in my opinion, was having to find that missing angle measure, right, the missing angle measure for a law of cosine. So we've got a non-right triangle, right, a non-right triangle, and we've got to purposefully determine what the measure of that largest angle is. So let's go ahead and take a look at our first one. In our first one, we know that we can solve for x by using our inverse operations. If these terms on right are connected by addition or subtraction, we can add or subtract to, right, isolate that x term. And so basically, we're subtracting these terms over. We could have combined the terms first, it doesn't matter. But the point is that we've used addition or subtraction to isolate that variable term. Now we're going to use multiplication or division, right, to get the x term by itself. And so now we're going to go ahead and undo that multiplication, just like we'll have to do in a minute with our law of cosines problem. So division undoes the multiplication. That gets our x term alone. And finally, we'll undo the cubing. What's going to undo cubing, right? What's going to undo cubing? Ian? Cube rooting, absolutely. And so if we're raised to this integer exponent, right, we can undo that cubing by cube rooting. So it looks to me like x will be given by the cube root of -1. And it turns out that this does exist as a single real answer. The cube root of -1 says what multiplied by itself 3 times equals -1. Oh, -1 cubed equals -1. Raise your hand if you already had that. So who already had x equals -1? That's right. Awesome. So the point of that question was, in order to solve for this unknown angle measure x, I've got to use addition or subtraction to isolate that term that includes my cosine of x. Then I'll utilize division, right, to undo that multiplication of -2 times 42 times 35. And lastly, right, just like we undid cubing, we'll undo the cosine. So the point of this question was order of operations. So I did in one step in class, I subtracted over the 42 squared minus the 35 squared, and you don't have to do it that way. It's just I do it that way so that I avoid making a mistake with my order of operations. Next, I went ahead and undid that multiplication. So to undo multiplication, what operation do we use? We use division. That's where we got that mammoth fraction when we went and used our calculators, right, in class in order to find that missing angle measure. We're going to divide by opposite of 2 times 42 times 35. And finally we'll get our cosine of x alone. So I'm getting cosine of x equals 70 squared minus 42 squared minus 35 squared all over -2 times 42 times 35. Finally, we're in a position where we can get that x alone. Just like we had to undo cubing to solve for x in the first, we have to undo the cosine function. Well, what undoes the cosine function? How am I going to get that unknown angle measure x alone? Aaron?
Use the inverse cosine?
Absolutely, thank you. So I know that my result, x, right, angle measure, will be given by the inverse cosine of all that. Holy cow, we've got a lot going on there. So I'm going to go ahead and use color-coded parentheses for my numerator and denominator just so I can enter this correctly in my calculator, right? Several of you were getting errors in your calculator during the quiz, right? And I couldn't help you with the entering. That was one of the things we were quizzing, that we're able to go all the way and find that angle using law of cosine. So what's in my numerator? In our numerator, we've got our 70 squared minus 42 squared minus 35 squared. In our denominator, we have opposite of 2 times 42 times 35. And I can't wait to try. So let's go ahead and use our graphers. We'll see if we can't avoid producing an error message in there, right? Domain, let's see. So inverse cosine would be second cosine. And then a left paren to open up my numerator. There's my blue. There's my first blue parenthesis. Here we go. Ready? 70 squared minus 42 squared minus 35 squared. Close numerator with the right paren divided by There's my left green parenthesis, opening up the denominator, opposite of 2 times 42 times 35. Close my denominator with the right green parenthesis, and then close my inverse cosine input. It should all match. I've got 1, there's my pair, there's my pair. Pinch of salt over the shoulder, and voila! 130.54 degrees it looks like, so that's pretty sweet, and I didn't get an error message. I'm feeling pretty good about myself. 130.54 degrees. And raise your hand if you already generated that. So did anybody go to the end without an error? Hey, that's great! Many of you did on your quiz as well, and so good job. I stress the importance of our order of operations there and being careful with your inverse cosine domain here. Awesome. What questions do you guys have on today's Bellwork? Great. Then let's go ahead and take a look at our green sheet to complete numbers 3 through 6. And so what? Well, for our exact values worksheet last class, we were able to determine the exact value of angle measures in between 0 and 360 degrees using our acute angle special triangles for 30, 45, and 60 degree angle measures. So everybody find your green sheet. We'll be able to use this green sheet so long as our angle measure corresponds to a special triangle, 30, 45, or 60 degree angle. The key is determining which it's going to be, and then we can use our green sheet to get the magnitude of sine or cosine. The key thing we'll have to be on the lookout for is if we have to add a negative sign or not, based on the quadrant in which the terminal side of my original angle lies. So let's take a look at 135 degrees. So 135 degrees, we're spinning, stop. The cosine of 135 can be evaluated exactly without a calculator by determining a reference angle. Everybody, let's find that reference angle. Remember, the reference angle is the measure of the acute angle that separates 135 degrees from the nearest x-axis. So, does 135 degrees correspond to a 30 degree, a 45 degree, or a 60 degree angle based on that reference angle that I've drawn in blue? Which is this going to be? Anna?
45.
A 45 degree angle, absolutely. My blue reference angle is 45 degrees. Therefore, the sine and cosine of 135 degrees are the same magnitude as the sine and cosine of 45 degrees. Everybody find it on your green sheet. So what's the cosine of 45 degrees? Go ahead and tell the class exactly. Blake?
Root 2 over 2.
It is correct. Root 2 over 2. The only difference is that we may have to add a negative sign depending upon the quadrant which my original angle 135 degrees lies. It looks to me like I'm in quadrant 2. Is cosine connected to the x or the y coordinate of any point? Is cosine connected to the x or the y coordinate? Hans? To the x coordinate. Now, our x coordinate's positive or negative in quadrant 2. Jacob?
Positive.
X coordinates are positive? Negative. Therefore, my cosine value must be negative. And that's why we get negative root 2 over 2. Good job. Thank you, guys. Everybody find the sine of 45 degrees. Or find the sine of 45 degrees. And what's that? Cody?
Root 2.
It's also root 2 over 2. Good job. The only thing is we might have to add a negative sign, right? In quadrant 2, where 135 lies, is sine positive or negative? Oh gosh. So sine is based on x or y coordinates. Rachel? Y coordinates. So is sine going to be positive or negative in quadrant 2? Rachel? Still positive, absolutely, because sine is based on y coordinates. Y coordinates are positive in quadrant 2. I don't need to add a negative. Do you guys see? All right, let's do another. Spin, 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 210 degrees. Stop. Let's find our reference angle. Does 210 degrees correspond to a 30 degree, 45 degree, or 60 degree reference angle that I've drawn there in blue? Carson? 30 degree is correct, which means that the cosine and sine of 210 degrees are the same magnitude as the cosine and sine of 30 degrees. Everybody find it. What's the cosine of 30 degrees on your green sheet? Get ready. Caitlin? Root 3 over 2 is the cosine of 30 degrees. The question is root 3 over 2 the cosine of 210? Well, it's going to be the same magnitude, the same size. It's just a question if we need to add a negative. So everybody take a look. Well, we need to add a negative for cosine, given that 210 degrees lies in quadrant 3. Do we need a negative there? Jacques? Yes, how come?
Because X values on quadrant 3 or 4 are negative.
Absolutely. In quadrants 2 and 3, x values are negative. 210 is in quadrant 3. Absolutely. So we need to add a negative. We had to do that purposely on our own. We got the magnitude of cosine of 210 by looking at our green sheet and getting the magnitude of cosine of 30 degrees, our reference angle in blue that we drew. But we had to purposely add the negative to show, because we ended up in quadrant 3 and x coordinates are negative in quadrant 3, cosine is connected to the x coordinate. Great. One to go. Sine of 210. Sine is based on the x or y coordinate. Right? Sine is based on x or y. Casey?
Y.
Y coordinate. Good. So in quadrant 3, is my sine of 210 going to be positive or negative in quadrant 3? Kendall?
Negative.
Negative. Good. Y coordinates are negative in quadrant 3 and quadrant 4, those lower quadrants beneath the x-axis. So this is going to be a negative value. What's its magnitude? The same magnitude as that 30-degree reference angle Carson told us about. Everybody find it. What's the sine then? The sine of 30 degrees. Kenzie? 1/2 is correct. So we've got our negative because we're in quadrant 3. We've got 1/2 because our reference angle is 30. Put it all together and the sine of 210 is negative 1/2. Everybody good? All right. Let's go ahead and try those last two on your own. I'm going to pause the recording right now and I'm going to call on you to share. Okay, ladies and gentlemen, let's come together and check the cosine of 240 degrees. Go ahead and share with the class when I call on you. Cosine of 240 degrees for number 5. Cody? Negative 1/2. Good job with the negative. Raise your hand if you have the same as Cody. Negative 1/2 is the cosine of 240. Nice job. Hands down. Sine of 240. What'd you get for the sine of 240 degrees? What'd you get for that? Caroline?
Negative root 3 over 2.
Negative root 3 over 2. Good job with the negative. Raise your hand if you have the same as Caroline. Negative root 3 over 2 is correct. Good job. Way to go. And the last two, cosine of 330. What did you get for that, Jarrett?
Root 3 over 2.
Root 3 over 2 and positive because x coordinates are positive in quadrant 4. Nice job. Raise your hand if you have the same as Jarrett. Root 3 over 2. Yeah. And the sine of 330 degrees. What did you get for the sine of 330 degrees? Mark?
Negative 1 over 2.
Negative 1/2. Raise your hand if you have negative 1/2 for the last one. Nice job. Thank you, guys. What questions do you have about your reference angles? All right, using your green sheet to get the exact value. Nice job. You'll see that more and more in FST. Okay, so I'm going to go ahead and pause the recording. We'll do our homework check, and then we'll get your quizzes back. Ladies and gentlemen, today we're going to use the unit circle and our Ferris wheel model that you used to generate those directed horizontal and directed vertical distance measurements last class to generate the sine and cosine graphs as a function for any angle input. And so we're going to see what the graph of our new parent function, y equals sine of x, and y equals cosine of x looks like. And then we're going to compare similarities, differences, and state key behavior components like domain, range, stuff like that. All right, so let's go ahead and take a look at our sine and cosine as functions, right? Not just as values, like our exact values worksheet, but now consider any angle input, right? Not just those special 30, 45, or 60s. The last two class periods have given us some insight into how sine and cosine values can be found for any angle, not just acute angles and triangles. Today we'll look at sine and cosine as functions with the domain of any angle and look closely at the behavior of the graphs of these functions. It's important to note that sine waves, as we call the graphs of sine and cosine, appear in a variety of real-world applications. Think about the tides and the depth of water as a function of time throughout the day. The water comes in during high tide, reaching a maximum, and then the water depth decreases as the tide goes out, and so on and so forth. Take a look at this graph of average daily temperature as a function of the time of year and the corresponding hours of sunlight. Look at this. This is what we call a sine wave. And notice how the daily temperature, right, the daily temperature graph there with the kind of the squiggles closely follows the length of the day, the number of hours of sunlight, but they're not in exact sync. You know, they're set off with what we'll call a phase shift. And so we're going to be developing some key terminology as we work through this unit and again next year in FST. And so we've got a variety of real-world applications for sinusoids or sine waves. Last class we measured vertical distances and horizontal distances from that point A on our little Ferris wheel model. we're going to go ahead and use the values from our table to generate these parent graphs on your note sheet. So you completed this. Recall that our column 2, the calculated vertical distance, was given by 5 times the sine of angle of rotation, and our directed horizontal distance was given by 5 times the cosine of theta. Because we completed this and turned it in, I went ahead and included a copy for you in your notes. We're going to be using our pen or pencil tip now to carefully plot points based on x coordinate as the angle measure, and then our directed vertical displacement is going to be our y coordinate first when we develop the sine graph. So let's go ahead and carefully sketch this. First thing we're going to do is take a look at our axes, and we're going to carefully plot our column 1, our angle, column 1. So we're going to plot our directed vertical displacement from the origin. We're going to carefully plot that together. So let's go ahead and look and see if we can't do our first plot. So we had 0 degrees is going to be paired with 0 centimeters above the origin. So we have the key point 0, 0. Everybody go ahead and carefully plot that. Next, we had 30 degrees of rotation, and that corresponded to a vertical displacement of 2.5 above the origin. So we're going to plot the point 30 degrees, comma 2.5. Everybody carefully do that. So it looks like this goes by 15, 30, 60, 90. So 2 ticks, 30 degrees, 2.5. Everybody, so 30 degrees is 2 ticks, comma, paired with 2.5 on vertical displacement. Next, 60 degrees, 4.33. So 60 degrees was 4.33. About there. 90 degrees is paired with 5. That was when our point A was all the way up at the top of the Ferris wheel. Then we went ahead another 30 degrees, went to 120. 120 is going to be paired back down to 4.33. So that's about here. 150 is going to be paired with 2.5. So here we go. 150 is going to be paired with 2.5. 180 is going to be down at 0. Let's keep plotting. 210, negative 2.5. 240, negative 4.33. 270, negative 5. 300, negative 4.33. 330, negative 2.5. And 360, we're back at a vertical displacement of 0 centimeters above or below the origin. Take a minute and make sure you have your values plotted. Can you see a pattern here? Could you extend this pattern into the negative angle rotations? Could you extend this pattern to the left? Yeah, if we were to extend this sine wave and follow that pattern to the left, we could complete another cycle in the negative direction. So everybody, let's carefully do that. So we're going to go ahead and go back in the other direction. So again, back 30 degrees, down 2.5. Everybody carefully do that. 60, 4.33. 95. Whew. Tough stuff. After you go ahead and extend your points then in the negative direction as well. Seeing some carefully plotted points, some nice scatter plots. Now let's go ahead and connect the trend of scatter plot points and make a nice smooth curve, continuous function for all real input x angles. And so let's go ahead and connect them. Here's the moment of truth. Here we go. So everybody try and draw that. we've just made our first sine wave, and this goes forever in both directions. Can I fix that? It's gonna be tight. Not looking so good. Next, we're going to go ahead and graph our angle of rotation and then pair it with our third column. That is our measured directed horizontal distance. That's to the right or to the left of the origin. So that came from our 5 cosine theta, right, calculation. Then in the fourth column, let's carefully plot those points. So everybody, here we go. 0 degrees is paired with 5 centimeters because after rotating our point A 0 centimeters, we were all the way to the right. We were 5 centimeters to the right of the origin. 30 was paired with 4.3. 30 was paired with 4.3. 60 is paired with 2.5. 90 back at 0. 120 negative 2.5. 150 negative 4.33. 180 negative 5. 210 negative 4.33. 240 negative 2.5. 270 0. 300 2.5 positive now. 330 4.33. 360 back up at 5. This looks very similar, right? It appears that I have that same oscillating behavior up to a maximum and down to a minimum, up to a maximum, down to a minimum. Can we extend this behavior to the left for negative degree inputs as well? Yeah, let's just keep going. We don't have it in our chart, so let's go ahead and keep going by extending the pattern. So here we go. By golly, that's going to be better. The moment we've all been waiting for when we take and follow this trend exhibited by the points in our scatter plot and connect it in a nice, smooth function, right? Continuous function for all real inputs, x, positive or negative input angles. Here we go. Oh boy, it's going to be way better than last time, Casey. I feel it. I need that one, just a mulligan. Shake the dust off. Oh yeah. Here we go, and that goes in both directions forever and ever as well. Awesome. So what equation is displayed on these graphs? Well, for the first one, we went ahead and plotted our angle of rotation, comma, directed vertical displacement. That came from our calculated second column of 5 sine of theta. In this case, it's going to be 5 sine of x. And so our first green graph has equation y equals 5 sine of x. Our second equation, the red graph that I made, has equation y equals 5 cosine of x. So when we took our vertical displacement measurements and plotted them, we generated the sine function. When we took our directed horizontal distances and plotted them, we got our cosine parent function. Now we're going to go ahead and use our graphers here to verify our equation guessing. So let's go ahead and go to our graphers. We want to make sure that our mode is in degree mode in our graphers, and we're going to all get the same window. So let's go ahead and set our window manually. Everyone, let's go ahead and do our x window from negative 360 degrees to positive 360 degrees. Bless you. Let's go ahead and do our Let's do our y window from negative 5.5 to positive 5.5. So if we graphed in our y equals menu, if we graphed 5 sine x to verify our equation, 5 sine of x close input, my calculator would show a blue graph that should resemble our first picture, right? So how do we do? Does that look like a sine wave from our first picture? For me, that was the green one, right? Isn't it? Yep, there's my green one. Well, my calculator does a little bit nicer without a graph. Yikes. Let's go ahead and add in y equals sine of x to our graphing window, but let's do it for our second equation, y sub 2. So let's go ahead and graph y equals sine of x on the same screen. So I'm going to go ahead and do sine of x on the same screen. Without the 5, it'll just be 1 sine of x. And compare the graphs. So everybody, we've entered 5 sine of x in y1. In y sub 2 equation, we've entered just sine of x, right? What effect does that multiplier of 5 have on the graph, that first blue graph, right? How does that compare with y equals 1 sine of x in red? How do those graphs compare? How are they connected? Rachel?
When you read the values of sine x, you just multiply them by 5.
Absolutely. The y values of my sine of x function are multiplied by 5. They're 5 times as tall. So for a given x angle input, right? If I take the y coordinate on sine of x and multiply it by 5, I get the corresponding picture for y equals 5 times of x. Exactly. So what does the multiplier 5 have on the graph? It makes it 5 times as tall. Right? 5 times as tall. Nice job. Let's go ahead and do the same thing, but now with cosine. So everyone in our grapher, let's change our y1 now to 5 cosine of x to see how we did with that second graph. For me, that was the red one. And we'll make our parent function plain Jane cosine of x. So let's go ahead and do 5 cosine x and compare that with cosine of x. Let's see how we did with our graph. Same window. Fourth quarter. All right, let's go ahead and take a look at our 5 cosine x and compare that with 5 sine of x. And so 5 cosine of x, 1 cosine of x. So there's our 5 cosine of x. Here's our 1 cosine of x. Yeah. Oh, and it's there twice now. Good. Double your pleasure, double your fun. Double your something with double the gum. And there we go. How do we do? Well, how did our red graph do? That was our cosine one. We guessed 5 cosine of x, and that looks a lot like 5 cosine of x. Here comes 1 cosine of x. How do the graphs compare? Well, Rachel told us last time that 5 multiplier took the y coordinates of sine of x and made them 5 times as tall. Well, the same is going to be true here for my cosine function. Let's go ahead and state that as well. So what happened with the 5 multiplier? Well, it made the graph 5 times as tall. So 5 times as tall. I think I'm going to add that in my other one too. 5 times as tall. That's pretty sweet. All right, so we've got some key important properties with the sine and cosine functions. This is a big deal. You have now constructed your first sine waves, right? Your first sine waves. Whether it's a sine or cosine function, it's still referred to as a sine wave, and they all share that kind of similar behavior where they oscillate back and forth between some maximum and some minimum value forever in both directions. These graphs are both periodic. A periodic function has a graph which can be mapped onto itself by a horizontal translation. That is, a portion of the graph repeats itself over and over. If we look at this picture, right, we can see that if I were to grab onto this portion of the graph and slide it over, right, slide it over like a transparency, it would fall upon its own image. And I can do that an infinite number of times with a periodic function. So some segment of the graph repeats itself over and over. The number of units it takes to complete one full cycle is called the period p. And we're going to be doing a lot of that with our graphing in the next several days. These types of graphs are called sine waves. Both sine and cosine functions can be called sine waves, even though cosine, right? Even though cosine is a different function. What transformations would make the cosine function the same? Well, gosh, these look similar, don't they? They look similar, but not the same. What would make the cosine the same as the sine function? Could I translate that and make them the same? What would I have to do to this cosine function to make it the same as the sine function? See the picture? What could I do? What could I do to make those match? Rachel? That's all right. Look at this one. All right. So what could I do to that? How could I shift that so that it falls on top of this sine one? Just in words. Well, definitely, right? If I change my equation to sine of x, I can get that graph. If you guys could grab onto this, right? If you could grab onto this, math man and math woman, you grab onto this with your hands. How could I shift this so that it falls upon the sine x graph? How could I shift this so it falls upon the sine of x graph? Hannah?
But so it's intersecting 0, 0.
Absolutely. If I grabbed onto this, right? If I grabbed onto this graph and moved it enough so that that key point here, this x-intercept, was now at 0, 0, right? Then it would fall upon the image of the sine graph. Is that the only way? Well, no. What if we had gone ahead and, what if we grabbed onto the sine graph and moved it left, right? We have to go a little bit farther, but we see that we'd eventually get this x-intercept to fall upon 0, 0, and then we have the same one as well. So a horizontal translation of the sine graph, right, will create a cosine graph, and a horizontal translation of a cosine graph will eventually create a sine graph. That's pretty neat in a math sort of way. And lastly, these graphs will always have both a maximum and a minimum value, right? And that's going to be a big deal when we're modeling real-world phenomena. All right, so let's go ahead and get our parent functions then. Your graph sheet has sine of x being a solid line and cosine of x being a dotted line. You don't have to do solid and dashed. You could do color-coded, right? You could do 1 in pencil, 1 in pen, however you want to handle it. I'm going to go ahead and do sine of x. I'm going to do sine of x in green. And I'm going to do cosine of x in blue. So let's go ahead and carefully get our parent functions now. We're going to do our regular parent functions, 1 sine of x and 1 cosine of x on your note sheet. Everybody find it. This is the point of our discussion today. So here we go. Sine of x starts at the key point 0, 0. So we're going to go ahead and start with 0, 0 for our sine of x function. At 90 degrees, we reach our maximum, and that is 90 degrees, comma 1. 1 is our maximum y-coordinate. At 180 degrees, we're back at 0. 270 degrees, our sine function is down at -1. And 360 degrees, we're back at 0. We can extend this pattern to the left or to the right of the origin, right, for negative angle inputs as well. So here we go. At negative 90 degrees, we're at our minimum, -1. Negative 180, we're back at y equals 0. Negative 270 paired with y equals 1, our maximum value. And then negative 360, we're back at our x-intercept. So here we go, a nice, smooth sine wave. Sinusoids or sine waves don't have any corners or kinks. They don't have any angles like absolute value v's. They're nice and smooth, right? More like the curved parabolas u's. And so here we go, a nice, smooth wave. And that pattern goes forever and ever in both directions. Next, we'll go ahead and plot our cosine function. I'm going to go ahead and do that in blue. You can use different colors or line styles as you see fit on your note sheet. Key thing is that the cosine function, the y-intercept is not 0, 0, it's 0, 1. It starts out at maximum displacement away from the origin. That's when we haven't spun that point A on my Ferris wheel at all. It's the furthest away from the origin that it will ever be. So the cosine function starts at a max, not at an x-intercept. Here we go, 0, 1, everybody plot it. 90, 0 is the x-intercept. 180 is at a minimum -1 value. 270 is paired with 0, and 360 we're back up at 1. Let's extend that pattern to the left as well. For negative angle inputs, -90 is paired with 0. -180 we're down at a minimum, -1. -270 is paired with y = 0. And at -360 we're back up at a maximum. We're going to carefully connect those points now in a nice smooth sine wave, even though this is a cosine function. You can still call it a sine wave. Nice, smooth, and well-behaved, no corners or kinks. Where's my second one? Always better, Casey. Gosh darn it. Some key features are in common, right, for sine and cosine functions, and some key things are different. Let's go ahead and outline the domain and range for each of these. And so recall from our function behavior unit way back at the beginning of the year, domain refers to the set of allowable x value inputs that we can plug into my function and correspondingly pair with an output. And so my domain in each case is all real x's. They go on forever in both directions. So all real x inputs is my domain for each. So domain is again all real x's in each case. The range, however, is restricted. These functions are what we call bounded. Right? There's a maximum y value attained above and a maximum y value attained below, so they're bounded. The maximum y value attained in each case for my parent functions is y = 1. The minimum is y = -1. So we could write that using inequality notation if we wanted to just say -1 is less than or equal to y is less than or equal to 1, and that's true for each function. So my range, my output y values oscillate between -1 as the minimum value and +1 as the maximum value, forever and ever in both directions. The x-intercepts of the sine function occur at x = 0 degrees, and then again at every 180 degrees in both directions. So we can kind of label that with shorthand notation by stating our first one. We'll say our first one, our x-intercept is 0 degrees, and then plus or minus 180 degrees in. And so we start at x = 0 degrees is that key first point, that key starting point, 0, 0. And then if we go ahead and step 180 degrees in either direction, we'll get on another x-intercept forever in both directions. The x-intercepts on the cosine function are different. Here my x-intercepts on the cosine function begin at, or there's one at 90 degrees, and then again, still every 180 degrees in every direction. So we can go ahead and say that these start at 90 degrees, and then plus or minus 180 n for integer n values. And you can continue landing on x-intercepts forever to the left and to the right. The y-intercept is my key starting point. So for the sine function, we need to remember what Hannah told us earlier. The sine function starts at key y-intercept 0, 0. So that's a big deal. And that's the main difference between these graphs. So while the key start value or y-intercept for sine is 0, 0, the key starting point for cosine is at a maximum 0, 1. That's the main difference between these two functions when we're going to start graphing next class. So my sine function on the y-axis, its start value is 0, 0. The cosine function on the y-axis, right, its start value is 0, 1. Everybody see that? Lastly, the period of a sine wave refers to the length of time, the length of units that it takes to complete one full cycle. And so you could start counting anywhere you like, right? If I wanted to consider the period of the sine graph, I could start at this key point, start value 0, 0, and then see how long it takes to complete one full cycle, and then end up at that same exact place in its behavior. It looks like to me that it takes more than 180 degrees. it's true that we're back at an x-intercept after 180 degrees, but have I completed one full cycle of behavior? No, I have to complete an up and then a down and then be back on my way up through the origin, right, up through the x-axis rather, like I was there to complete one full cycle. So it takes not 180 but 360 degrees to complete one full segment. This is a period 360 degrees, and now I can slide this segment along, fall upon its own image over and over again in both directions. So that's why it's called a periodic function. The period of in this case, degrees it takes to complete one full cycle is 360 degrees. How is that different with the cosine function? How long does it take the cosine function to complete one full cycle? Well, let's see. If we start at this key point, we can start at any point we wanted. But if I start at this key point that I already have squared here, it takes how long to get back up to that key point? Well, by golly, again, it looks like it takes 360 degrees. So the period of each of these parent functions is the same, and that's 360 degrees. Think about our Ferris wheel model, and why would it make sense that the period of these functions would be 360 degrees? What's special about that 360 degree number? What does that 360 degrees have to do with anything? No? New? Me. Jacques.
When you get back to 0.
Absolutely. That's when you complete one full circle and get back to your starting point on the Ferris wheel, right? One full circle is that 360 degrees. Well, guess what? 360 degrees is the length of time it takes to complete one full cycle on my periodic sine graph as well. You guys are killing it. All right, one thing to go, and that's to verify what we'll call the Pythagorean identity. So what we're going to do is we're going to break up into columns, and then everybody's going to pick a different angle measure, right, in between 0 and 360 degrees. But to make sure we're not all picking the same angles in quadrant 1, we're going to go ahead and divide up. And so you guys are going to pick some degree measure in between 0 and 90 degrees for quadrant 1 value. You guys are going to go ahead and pick some degree measure, right? It doesn't have to be one of our exact value worksheets, right? It could be 147 in quadrant 2, right? So in between 90 and 270, go ahead and write that down on your sheet, pick that. You guys are going to pick some degree measure in quadrant 3 over there, and you guys are going to pick some degree measure in quadrant 4. Does everybody know which quadrant you're responsible for? It doesn't have to be one of our exact specials like 240. Make it some odd degree measure, because the Pythagorean identity is going to end up working for any degree measure, 0 to 360, positive or negative. But we're just going to do positive in your given quadrant. So everybody pick one. You can write it down, and we're going to go ahead and draw. We're going to go ahead and draw a ray that corresponds to that given rotation. So I'm going to go ahead and do mine in quadrant 2. So I'm going to go ahead and go here. I'm going to go here. And I'm going to pick 131 degrees. Now, you could have picked something entirely different, right? Quadrant 3ers are going to be picking numbers that are more like 206. Quadrant 4ers might have something like 339, right? And so on and so forth. Awesome. Now let's go ahead and connect my terminal side of the given angle, that point x comma y. Let's go ahead and connect that to the nearest x-axis. So I'm going to drop mine down as an altitude here and form a right triangle just like we did in our activity. Recall the x-coordinate of this point is given by the horizontal leg length of that right triangle. The y-coordinate of this point is given by the vertical leg length of that triangle. If this is a unit circle, like our activity from before, a unit circle has a radius that's defined to be 1. So what relationship exists between the leg lengths in a right triangle, x, y, and 1? Well, the same thing you used in middle school, but instead of using a, b, and c, you could write that relationship with x, y, and 1. And so what equation would exist between x, y, and 1? What equation would exist there? Joe?
X squared plus y squared equals 1 squared.
Awesome. But isn't the x coordinate of any point on the unit circle given by cosine of that angle rotation. So this x value is really cosine of theta squared plus the y coordinate is given by sine of theta squared, and I want to see if that does in fact equal question mark 1. So let's go ahead and take a look at that on our calculator. I'm going to do the cosine of 131 degrees. I'm going to square it plus the sine of 131 degrees squared, and I'm going to see if that does in fact equal 1. So big. It does. I get 1. What degree measure did you have? What degree measure did you have? Jarrett?
293.
293? That is in quadrant. Cosine of 293 squared plus sine of 293 squared equals, Joe, I think you got a winner. X squared plus y squared equals 1 squared. This is what we'll call the Pythagorean identity. So oftentimes we'll see that cosine theta quantity squared written in shorthand notation as cosine squared plus sine squared equals 1. Cosine squared theta plus sine squared theta equals 1. And that makes sense because the cosine of theta is just the x coordinate of my point after any degree rotation in the positive or negative direction. The y coordinate is just the value of sine of theta, and Joe told us that x squared plus y squared equals 1 squared, which is 1. You're just going to see that a lot. Okay, a lot of identities next year in FST and then in the pre-calc are based on the Pythagorean identity. So that's pretty sweet. All right, let's close up our discussion today. You guys are doing great. We're going to fill in the blank today. So for our closure today, we're going to fill in the blank, and then we'll have a little bit of work time. So the equation y equals sine of x measures the blank distance and starts at the ordered pair blank comma blank. So we're going to go ahead and use an ordered pair x comma y to complete the sentence, and we're going to think about it in our chart which the sine function came from. So think about what column we were using for our sine function when we generated its parent graph. For our second closure item, the equation y equals cosine of x measures the blank distance and starts at the key point ordered pair x comma y. Let's fill that in with values, and I'm going to call on you to share with the whole class. So please be ready. Okay, go ahead and share with the class. The equation y equals sine of x measures the blank distance and starts with the ordered pair blank. Casey?
Vertical.
Measures the vertical distance, good, and starts with the key ordered pair
0, 0.
0, 0. Raise your hand if you have the same thing as Casey for number 1. Sine measures the directed vertical displacement above or below the origin and starts with the key point 0, 0. Good job. The equation y equals cosine of x measures the blank distance and starts with the ordered pair what? Blank?
0.
Good. 0, 1. Thank you. And it measures the which distance?
Horizontal.
Horizontal distance is measured by the cosine function. Absolutely, you guys. Great work. So sine of x measures the directed vertical displacement above or below the origin. Starts at the key point 0, 0. That's my x-intercept or at the origin to start the party. cosine of x measures the horizontal displacement from the origin with our Ferris wheel. And that starts at the key point 0, 1 at a maximum. Nice job, you guys. For next class, we've got a hybrid assignment, so we got sum book problems, and we've got our 10.6b lesson master that talks about behavior, sine, and cosine. Don't forget your reading question 10.9. I'm going to go ahead and stop the recording and upload it to our Moodle site.